Now in the next part of the video, we will see how to make this code, make this OFDM MATLAB loopback compatible for antenna transmission. The antenna that we will be using is WERT 400 antenna. And when we check the data sheet of this antenna, we see that one of the center frequencies is at 144 megahertz and the bandwidth for accepting range is 118 to 160 megahertz, which is around 40-42 megahertz. So firstly, we'll check that what is the frequency spectrum for our signal. So to check the frequency spectrum of our signal, we will take the fast Fourier transform of the signal. For fast Fourier transform, I will use the inbuilt FFT function of MATLAB. I have to take the fast Fourier transform of the signal that is being transmitted, and the number of samples is the length of the signal. Since already we are plotting once, this when I go to plot, this will be the second figure. I now need to define the frequency spectrum, which will be until the length of this FFT result into whatever the sampling frequency that I'm using normalized. Now, when I plot, I will plot the frequencies and the absolute value of the FFT result. I will set the X limiter. I want to see the data from 0 to the maximum value of frequency in megahertz. I will put the title for the plot. It is FFT of the signal to be transmitted. And on the x-axis, I will be seeing the frequencies. So now if I see the spectrum, I won't because Fs has not been defined yet. So let us define the frequencies that we will be needing. Now, as you remember, we will be using the same block diagram that we had used for demonstrating the tool. In this block diagram, when I open the RF data converter IP for customization, I'll see an interpolation factor 2 has been defined here. For the ADC, decimation factor 2 has been defined. And for the DAC, interpolation factor 2 has been defined. So using the same framework in this MATLAB as well, I will define a sampling frequency for the board, which for now I'll be setting as 1.47 gigahertz because this is the sampling frequency that we have used in the previous example. I will be setting the interpolation factor as 2, and then the effective sampling frequency will be We also have seen the center frequency we desire is 144 megahertz. So I'll set that as well. And now we are good to go to check the frequency spectrum of the signal that we are going to transmit. Now we see that the signal has bandwidth up to more than twice of this, twice of 276 megahertz. And we want it to be around 40 megahertz. So the first adjustment that we can do is increase this oversampling. If I increase it to 4, let's see what change happens. If I increase it to 4, the spectrum shrinks to approximately half. Let me shrink it even more. I'll use oversampling 8. When I use the oversampling 8, the spectrum shrinks to around 120 megahertz. So the second thing that I can do is change the sampling frequency. Now, in order to use sampling frequency below 1.47 gigahertz, these are the frequencies available for which register files have already been defined. Out of these frequencies, I'm choosing 491.52 megahertz for the board. That means effectively around 245 megahertz of sampling frequency. Let me check what happens when I use that frequency. Now, when I define the sampling frequency to be 491.52 megahertz, I see that the spectrum is around 42 megahertz effectively. So this is what I required. The second part is now modulating the signal and putting the center frequency around 144 megahertz. I'll need to save the signal at the last, so I've shifted this part of the code to the last. Now we'll modulate the signal. To modulate the signal, we will just multiply the signal element wise with e raised to power j omega c. For this part of the signal, we will just element wise multiply with e raised to power j omega c and t. So this is the modulated signal. Let's check the spectrum for the modulated signal. I don't need to define the frequency scale again. And this is FFT of the modulated signal. So when we check the FFT of the modulated signal, oh, we need to change the figure as well. This is the third figure in this code. So here it is. The signal still didn't modulate. Okay, I haven't taken the FFT for the signal. So when I take the FFT for the signal, now we'll see the modulated signal. And here we see this signal has been modulated to around 144 megahertz. And the frequency range is within what we desired. A little more than that, but the main lobe is within the frequency spectrum. So now we have made the signal adjustable to what we need for the antenna. We'll save this TX signal new. So the changes that we needed to do in the hard OFDM transmitter have now been done. Now we will move on to the hardware part. In the hardware part, firstly, I'll load a new signal. I'll reduce the number of samples since the number of samples now I have are 3888, which are approximately 4 times I had last time. So I'll just use 8 samples here. Now let's define the frequency components here as well because I will be checking the frequency spectrums here. So I'll define the same frequencies in the hardware code as well. Now let's check the frequency spectrum for TX hardware signal. Spectrum for I can use the same way to plot the signals. This will be the first figure, and I need to plot the signal. Let's check the frequency spectrum for this. So we see that the signal that we generated in the OFDM transmitter, it is the same signal. Now for the next part, I will be checking the spectrum of the signal that I have received. I can copy the same way that I have been seeing the spectrums. This will be the second figure in this code, and I need to see the spectrum for this. Uh, I can run the code until this line. This is the signal to be transmitted. I'll change the code here as well so that there is no ambiguity. This is the 50 of the signal received. I'll run it again. This is the signal to be transmitted, and this is the received signal. So the received signal too has the same center frequency and the same bandwidth. So I know that I have received the correct signal. Now the next part is to demodulate the signal frame by frame. For that, firstly, I will define a vector which is of the same length of the data to be processed. Now, to demodulate it frame by frame, I'll take one frame from the data to be processed. I will demodulate it by multiplying with e raised to power j omega ct. So for that, I will take one frame at a time. length of data to be processed. The length of data to be processed is the length of TX hardware, which is 3,888 samples multiplied 8 times. So 1 frame of DEM is 1 frame of data to be processed element-wise multiplication with e raised to power j omega c2. Since I am using 1 frame at a time, so I'll take the size of a single frame. And now I'll check the spectrum of the demodulated signal. Again, I can use the same way to check the spectrum. This is the third plot in my code. And I need to check the spectrum for DEM. And the length is length of, I'll check for a single frame of DEM of the demodulated signal. Yes. And I'll run it until here and see what do I get. This is the signal to be transmitted. And this is the demodulated signal, which is back to the baseband that we initially had. Now this demodulated signal can be processed and plotted in this loop. For that, I need to give the demodulated signal here. I need to give the demodulated signal inside the loop. Now we need to take care that our single frame is of size 3,888. And for needing 3 frames, I'll at least need size of 12,000 samples. So I'm arbitrarily uh, taking the number of samples to be 12,200. I'm just making sure that I have 3 samples at a time. And one more thing to note here is the initial signal is 1 cross 3,888. And right now, DEM is of 3,110 cross 1. So I'll need to take the transpose of DEM so that my initial signal and demodulated signal are in the same phase. So the hardware part is done. Now we will move on to the receiver in the next video.